Welcome to the modules lesson. Crudely speaking, a Haskell module is just a collection of related functions, types, and type classes that can be imported and used in your code. But they are more than just that. Modules allows us to structure, reuse, and maintain our code and environment. In this lesson, we are going to learn how to import modules in different ways to control our environment and namespaces. Then we are going to learn how to create our own modules. And finally, we're going to learn about the Prelude and the standard libraries. Because by now we already started to feel more comfortable in Haskell, depending on the subject, I'm going to just code or show slides. In this case, it makes more sense to just refactor code. So let's do that. Let's get started. Let's say our app needs to manipulate files and folders. We can use a module called system.directory that has a bunch of functions, actions, and types related to file and directory manipulation. To import this module, we use the import keyword followed by the name of the module. In this case, system.directory. You can see that the Haskell language server already suggests an autocompletion. And there you go. Importing modules must be done before defining any functions. So imports are usually done at the top of the file. By adding this line of code, we gain access to all the functions, actions, type, and type classes of the system.directory module. You can check everything that comes with this module here. We go to google.haskell.org and search for system.directory. We click here in the module system.directory and we get a short description, a full description, and all the code that it provides. One of the functions it provides is called list directory. This function lists all the entries in a directory. It takes a file path and returns an IO of a list of file paths. Let's see what a file path is. It's just a type alias for string. Perfect. So we can go back and test this. If we say we can use this and say list directory. And the dot is the current directory. So if we evaluate this expression, we get all the files inside our current directory. So let's use this in some way. Let's say that we decide to write a function to find files inside our current directory that contain a certain string as part of their name. For that, we can create the find. Let's close this. The find prime function that takes a string that is the search term we want to use, and it returns an IO of a list of file paths. Now we can create this function. It takes the search term, and we're going to do a couple of things. First, we need all the entries inside the directory. So we can call the list directory function. We pass the current directory and we bind the result of running this action to the entries binding. Now we have a list of file paths of all the files. In this case is all these, but they could be anything. So we have to filter them based on our search term. So we can say, okay, let found equals something, return found. And now we have to actually filter all these entries. We could easily create the filtering function ourselves with some pattern matching and recursion. it wouldn't be a bad idea to do it by yourself to practice. But realistically, this sounds like a common enough function to be available as a library. And it is. There's a module called data.list that contains dozens of functions to work with list. So let's import it. And now we have access to everything inside this module. One of the functions is infix of. This function takes two lists and returns true if the first list is contained anywhere within the second. So here we say that the first argument is Haskell and the second is I really like Haskell. So because Haskell is inside the second argument, it returns true. Anything else, it returns false. Perfect, exactly what we need. So we can use this to say, let's filter using some function the entries. This function is really simple actually because the hard work is done by the isInfix of. So we want to check that the search term is infix of whatever we pass as second argument, that in this case is the entries. And that's it. We can test this quickly. We can say find prime of .hs. So this should take a list of all these files and filter only the ones that contain hs. So we should get just a single file called main.hs. Evaluate. Perfect. And if we say, let's change this to main, we should get all the files. We can say new file, test me.txt, and another file to say test u.txt, just to be sure that it works for many files, and we have to check if it works for no files. So no files contain the string of a's. Perfect. Now to make this an actual Haskell program, the only thing we have to do is we have to create the main action. And this action is going to do a couple of things. The first thing is going to put string line saying provide search term. And then we are going to get line and save the result of running this action to search term. Now that we have the search term provided by the user, we can actually search for it using find st, and we bind the result of this found and put string line. These entries match your search. And that's it. So let's open a new terminal, compile our main.hs, and if we try to run this main program, provide the search term, test. These entries match your search, test me.txt and test you.txt. Perfect. Okay, so the function looks good, but it has a weird name. Why do we call it find prime? Let's remove the prime. And here we can see we have an interesting error. If we hover it, Variable node and scope, of course, we have to remove that find. Okay, now ambiguous occurrence of find. It could either refer to data.list.find or main.find. Okay, so the error is pretty clear. We have two functions with the same name. The one that we just wrote in our file, and also another that came imported from the data.list module. So the compiler doesn't really know which one we are referring to when we're using it. There are multiple solutions for this. The easiest one, of course, is to change the name of our function. If we can go back a bit and say, okay, rename this function and let's call it find entries, and the error is gone. But this doesn't solve the underlying issue that our environment is polluted with dozens of functions and types of both system.directory and data.list that we are not planning to use, which can cause all sorts of troubles. A better solution is to import a specific function or type class instead of the whole module. Let's do it that way. First, we change the find to the previous name. And now we have the error again. So we can go to the data.list import and say, okay, instead of importing the whole data.list, just import the isInfix of function. And boom, that's it. We just added the function that we needed inside those parentheses on the right of the import. This is so common that our language server already proposes us to use our imports that way. So we can click here and everything we actually use will be added to the import statement. That way we don't import more than what we need. And if we need to import more than one, we can just add it separated by a comma. For example, if we want to sort the entries before returning them, we can import the sort function from data.list and go to all filtered entries and say, okay, now sort them, please. Thank you. And there you go. The find function now takes all the files inside a directory, filters them based on the search term we provide, and then it sorts them and returns everything to the main function. That way we can keep adding the functions we need when we need them. Finally, if we happen to need many functions of a module, importing them one by one might be cumbersome, and we might end up with a huge list of functions that contain almost the whole module. For those cases, we can use the hidden keyword. For example, let's say that our find function is just one of many functions from data.list in our file. Instead of writing all the functions that we use, we can just say, okay, give me the whole module hiding the find function. So in this case, we are importing the whole data.list module except for the find function. And that's how you can control your environment while importing multiple modules. But there's one more case that we don't have a solution for right now. What if we import two modules that have functions with the same name? For example, we can import data.map module. This module has types and functions that allows you to store associations between unique keys and values. For now, don't worry about it. We will take a proper look at this module in future lessons. What is interesting about this is that both data.map and data.list provide a function called filter. Same as before, we have an ambiguous occurrence of filter because we could refer to data.list.filter or data.map.filter. We could hide either one of those. In this case, we are not actually using the filter function for map. But imagine we are writing a large program and we are actually using the filter of both modules. We want both filters in our code. In this scenario, we cannot change any of their names because we're importing both of them from modules we do not control. Now is when namespaces come in handy. Without all the jargon, a namespace is an environment created to hold a group of names. We've been talking about our quote-unquote environment as a single thing, a space that contains our functions, types, and types classes all mixed together. But thanks to modules, we can have different environments or namespaces. And it's easy as adding a single word to the input. This word is qualified. By adding the qualified keyword after the import, instead of adding all the code of data.map to our environment, we create a new one called data.map that contains all that code. That way, each time we want to use a function from this data.map module, we have to prepend it with the data.map prefix. So all that code is inside the data.map namespace. And as you can see, this solves our actual problem because now Haskell knows that this filter is from data.list and not from data.map. Because to actually use the filter from data.map, we have to write data.map.filter. There you go. And then we have to pass the parameters. To show how we could use the code from data.map, let's take that list of filtered and ordered entries and transform them into a map. Let's come here and let's create a new binding called found map. And there's a function to convert a list to a map inside the data.map library that is called data.map.fromList. As you can see, it takes a list of tuples. Let's open this information. It takes a list of pairs where the first value is the key and the second is the value. This is an example of how it looks. We have the values, the list of found are the values, but we actually need them with unique keys. So to do that, we can use functions that we previously learned. For example, the zip function that takes two lists and zips them together in pairs. And this zips function, we need the key. So to make sure they are unique, we can just use a list that goes from 1 to infinity. And we are going to say that this is a list of ints. And we need the second list, that is the found list. And that's it. This line converts the list of entries to a map of pairs that contain a unique key with a value of entries. Now we have to return this. So instead of returning found, we return found map. And we get an error because found map is of type map of int of strings. The first value is the type of the keys. The second is the type of the values. And Haskell couldn't match the type that we tell it we are going to return and the one that we are actually returning. So we have to change the type we are returning to data.map.map of type int and string. And there you go. Now it works. Let's try it out. Let's say GHC main compiles. Perfect. Now let's run it. Provide a search term. Let's put txt. These entries match your search. As you can see now, it's not just a list of strings, but it's a list of tuples with unique identifiers and the values. But it's still finding all the files inside our current directory that actually match our search term. Perfect. With this final feature, we gain complete control of our environment. Although writing data.map everywhere gets old pretty quickly. And if we qualify imports with longer names or qualify several modules, our code starts to get cluttered and harder to read. Luckily, Haskell allows us to rename the namespaces to a more convenient one. For example, we can go to this data.map module import and say as map. Now, instead of putting everything imported from the data.map module inside a namespace called data.map, it puts it in a namespace called map. So now in our code, we can drop the data dot. And it works the same as before. Notice that module names are capitalized. If you are renaming them, this new name has to be capitalized as well. And as a final tip, we can combine all these different techniques. For example, if two modules do kind of the same thing and don't have any name clashes, we could give them both namespaces the same name and treat them as if they came from a single module. This doesn't apply right now, but there's an import combination that does. Our find function looks pretty good, but one thing that bothers me is this map.map. I don't mind the map.fromList. Actually, I prefer it. That lets me know that fromList comes from the data.map module. But map.map is kind of redundant. Of course that the map type constructor comes from the data.map module. So let's combine a couple of imports to avoid this redundancy. We can go to the first import and say, okay, import the whole data.map module as map, but hiding the map constructor. And then in another separate import, we can say import data.map map. So by hiding the map type constructor from the qualified import and importing it separately, we essentially remove map type constructor from the map namespace and add it to our main namespace. So now we can remove this namespace and we get the final version of our code. Everything is the same, but now the signature of find is a bit easier to read. And that's pretty much everything about importing modules and managing your own environment. But remember, we said modules also allows us to better structure, reuse, and maintain our own code. Let's see how. For that, we will first remove everything and copy and paste some code that is a bit more complex. Before starting, let's remove all this. Okay, now we have a clean slate that we can work with. So let's create a game where the player goes through a forest and tries to find an exit before running out of stamina. First, we create the forest data type. Each forest could be either an exit or a trail that contains 3 different forests inside. The A represents the amount of stamina that is consumed when walking down the trails. This can be represented by any numeric value. So an example of a forest could be this structure. Here we have the level 1 forest that takes any type that is an instance of the or type class and the numeric type class. That's because we want to be able to compare the value to check if the player ran out of stamina or not. And also numeric because we want to be able to do mathematical operations on it. So we have the level 1 forest that starts with a trail that contains 3 different forests. And to run through the first trail, you have to consume 3 of stamina. If you happen to choose the first path, you have to consume 7 of stamina. And finally, you have to choose between these 3 options that the first one consumes 3, the second 4, the third 5, and it doesn't matter which one you choose, you will find an exit. As you can see, eventually you always find an exit. So the game is in that you have to find the exit before running out of stamina. So in the case you have 10 of stamina, you first consume 3, then 7, and then it doesn't matter which option you choose, you will die before the exit. That was the wrong path, so you need to try again with another path. In this case, you first consume 3 and then 3 again and then 3, so that's 9. You find the exit before running out of stamina. So we have our forest. Now let's create the movements the player can do. Because in each trail we have 3 options, we can create a data type of available moves that says, okay, the available moves are go forward, go left, or go right. Now that we have the available moves and the forest, we can actually create a function that traverses the forest based on the movement chosen by the player. So we create the move function. The move function is the one that performs the action of applying a movement to the current forest to get the new state of the forest. It takes a tuple containing the current values of the stamina of the player and the current forest. Then it takes the chosen movement and returns a tuple containing the new values of the stamina of the player and the new forest. So the first case is easy. In the case we find an exit, we return the same values as the ones we are given. Nothing changes. In the case that we didn't find the exit, we have to check which movement the player chose, and if it says, okay, go left, we pattern match the forest to extract the amount of stamina that it consumes and the left trail. And we return the amount of stamina the player has minus the amount of stamina the trail consumes and the left trail, which is our new forest. We do the same for the go forward and go right, and that's pretty much it. Now let's create the main action of our program. Let's close this so we can see it better. So, the main action of our program. We'll start by printing a message explaining the situation to the player, and then we start the game loop. The game loop function takes as parameter the current state of the game, which at the start, it's a hard-coded value of 10 for stamina and the whole level 1 forest. And then it defines what to do for all 3 possible cases. In the case that we found an exit, we just print, hey, congratulations, you found the exit, and that's it, the program terminates. If the player runs out of stamina, we print, hey, you ran out of stamina and died, and that's it, the program finishes. As you can see, we pattern match for the stamina and we check that the stamina is less or equal to 0. Finally, if neither of these 2 cases match, we still have stamina and we didn't find the exit. So we take both the stamina and the forest and print a message saying, hey, you have this much of stamina and you're still inside the forest. Choose a path. We use the getLine action to get the response from the user, and then we recursively call the gameLoop function with the result of applying the move function we just created to the current state of the game and whatever the user chose. We use the read function to transform the string that the getLine action provides to an available moves value. So this move function should return the new state of the game and provide that to the gameLoop function. And it will keep running until we've run out of stamina or exit the forest. That's it. Let's try it out. GHC main. You're trapped in a forest. Try to escape. Remember that you lose stamina with each step you take. You have 10 of stamina and you are still inside the forest. Choose a path, brave adventurer. Go left, go right, or go forward. Okay, just try it out. Go left. You have 7 of stamina and you are still inside the forest. Choose a path again. Go left. You ran out of stamina and died, and the program finishes. Perfect. And let's try to actually win. Go forward. You have 7 of stamina. Go left. I think this one, and go left. Congratulations, you found the exit. So that's our game. It's a pretty simple game, but imagine that you want to improve the game, make it bigger, make it have more options, etc. If you keep using this file, it will start to get bloated and big and unmanageable. So let's use modules to organize our code. We'll start with the most important of all modules, the main module. Did you notice that the file name is main with an uppercase? That was on purpose, because every Haskell project has to have a main module. If we go to the top, and here we write down module main, where we created our first module. This line says, okay, this file contains the main module where all this is defined. Now let's organize this. Let's make this a bit smaller. So we have code related to the actual forest. We have code related to movement and actions of the player. And we have our main actions. Let's start by creating a folder called forest. And inside this forest folder, we want to create a new file called level 1. That just, for example, in this file, we want to put everything related to the level 1 forest. As you can see, VS Code is already suggesting to write down module forest.level1 where. So let's click here. And now we have the name of our module. Notice that the name of the module is related to the position in the folder structure. So because this file is called level1hs, the name of the module is level 1. And because this file is inside the forest folder, the module starts with forest dot the name of the module. And that's why in the previous examples we have these systems.directories, was because the directory related code was inside the system related folder. So let's move the code. I want the data structure of the forest and the actual forest. I want it inside my forest.level1 module. Great, so let's save. And now we have an error here, of course, because everything related to forests disappeared. But it's here, so let's import it the same as we imported the standard Haskell modules. So we say import forest dot level 1. And that's it. Notice that the import also follows the directory structure. And here VS Code is suggesting that we write a more specific import. Let's click here. And this seems familiar. We already know that this is importing the function, but this is new actually. Here we're importing the forest type with all of its constructors. So here we could have written exit and just import the exit constructor, or do exit and trail to import both constructor. But if you're planning to import everything, you can just write double dot and all the constructors will be imported. So in the case you happen to change the constructors of forest, you don't have to change anything in the import side of things. Now let's move the movement related code to its own module. Let's create a folder called user, and inside user I want to create another folder called actions, and inside actions I'm going to create two files. The one we need is the move that we choose to name it move. You can name it however you want, but we want to put everything related to movement there. But I created this action folder because I think in the future I will want to provide other actions. So something like the attack HS to attack the enemies or whatever. This is just to complicate a bit the example, so our imports and exports are more interesting. So let's go to main, and here we want to take all this and put it here. Like this, it won't work because we don't actually have the name of the module. So let's create module named user.actions.move, where all this code is present. Perfect. We have the error, of course, that we don't have access to the forest, but we already know how to solve this. Import forest.level1, and in this case we want just the constructor. We don't actually need the level because we are not using it. Now let's go back to main and import user.actions.move. There you go. So following this procedure, you can have a better structure code and you know where to go when you want to actually modify it, make changes, or create new stuff. A cool thing that we can also do with exports is that we can say exactly what we want to export. So here, imagine we have a helper function. And this helper function is created just to use inside this module. We don't want to provide these functions to anybody else. So we can go to the module export and say export nothing. In this case, we're not exporting anything. So here we get an error because, hey, this module does not export this. So we can go here and say, okay, export forest with all its constructors, because we can also choose to export just forest without any constructor, or with just the exit constructor and not the trail constructor. In this case, we want all constructors, so we can just put the two dots and that's it. We still have an error because we don't have level 1 forest. So let's go here and say we also want to export level 1 forest. Now, if someone wants to access the helper function from the import, can't, because it says this module does not exploit the helper function. That way you can be free of creating anything you want inside the module, helper functions, helper types, whatever, and then just export the subset of the code that you actually want to be available for the end user of the module. Now, a couple of details. You can have only one module per file. You cannot create two modules in a single file. And also, modules are not first-class values. You cannot pass around modules within functions like numbers, other functions, and types. Now that we know how to work with modules, let's learn about the most famous of all, the Prelude module. When working with JCI or writing your own Haskell code, some functions are available by default. For instance, head, sum, length, etc. This is because those functions are part of a module called Prelude that is imported by default. The word Prelude means an introduction to something more important, which is the code and modules you will write. So the Prelude module provides basic function data types and type classes that the average developer might need for its code. Besides the Prelude, there are other standard libraries that are not imported by default, but are available to be imported without the need for you to download them separately. But we're going to ignore those for now. Let's explore this documentation a bit. So we have the name of the module here, Prelude, and its contents, as you can see, are arranged in categories, standard types, type classes, and related function, list operations, converted to and from a string, basic input and output. If we keep scrolling, we have a general definition of what the module is about, and then we start with the actual code. The first thing we have here is the bool data type. As we know, the Boolean data type has two constructors, false and true. And here we have all the instances that come with the module. Just by looking at this documentation, we know that we can convert Boolean to string, that we can compare for equality and inequality, etc. And after that, we have functions related to that type. In this case, we have three: the Boolean AND, the Boolean OR, and the Boolean NOT. We have the name of the function with its type, the fixity, and a short description of what the function does. And if that's not enough for you, you also have the option to look at the source code by clicking here. As you can see, this is how the Boolean AND operator is defined in the Haskell source code. We also have the Boolean OR definition here and the Boolean NOT. As you can see, these definitions are pretty much what you would do if you had to define them. Not of true is false, not of false is true, etc. But there are other definitions that use more advanced Haskell, like these ones. So at this stage, looking at the source code might or might not help you understand the function. Let's go back. And after these functions, we go to the next data type with explanation, constructors, all its instances, and functions, in this case just one, another data types, etc., etc. Also, you can take a look at the actual definitions of the instances if you click here, and you can see that the equality of bool has two methods, the equals and the not equals, and you can click here. You can see the type class, the fixity, and the explanation of this type class. And we can also look at the source code, and you will see that the actual definition of the equality type class is the same one we did in a previous lesson, with some extra details here, but we will learn about that in a future lesson. And that's pretty much it. Now, what I want you to do as a homework for this lesson is to read through everything provided by the Prelude. But in there's also plenty of stuff we didn't cover, and that depends on concepts we'll learn further down this course. So it's not required for you to understand everything. The objective is to have an idea of what the Prelude module provides, use it as a refresher of all the functions, types, and type classes we've been using so far, and to get used to reading the official documentation. And that's it for today. Make sure to do your homework, and I will see you in the next one.